All right, everyone, welcome. Thank you so much for waiting. We are going to get started with a few words from our PRC director, Dr. Swami.
Thank you, Sherry. Welcome to the short course series hosted by the Packaging Research Center. I serve as the director of the center. My name is Madhavan Swaminathan. We are located in Atlanta as part of Georgia Tech. And it's a beautiful day here in Atlanta. Spring is here, and I hope your part of the world, it's a beautiful day as well. Our heart goes out to those of you in India. We realize that the pandemic is really bad there, and we are with you as we go past this crisis. So today's presentation is going to be given by Omkar Gupte. So Omkar is a PhD. He just defended his PhD at Georgia Tech. His background is in material science and engineering. Ceremony is next week. So he'll be joining AMD. So today, the focus of the presentation is on a very, very important topic as it applies to packaging, which is the second level assembly. Being able to assemble the interposer onto, let's say, a printed circuit board. And in these short courses, what we try to do is to cover the fundamentals and also share with you what is the landscape as far as the work that is going on in this very important area. So with that, Omkar, the floor is yours.
Thank you, Professor. Good morning, afternoon, and evening to everyone on the line. Thank you so much for joining. The presentation today is about board-level interconnections, materials, processes, and recent advances. And for the short course, the objectives will focus on the basic concepts that are involved in designing and fabricating BGA-based or ball grid array-based board-level interconnections. Specifically, we'll be talking about first the classifying board-level interconnections and understanding the different structures for different interconnections. And then we'll go into the details of ball grid array or BGA type interconnections, talk about the solder paste printing process and the fundamentals of the process, understand the importance of system level reliability and the board level assembly and system level reliability, and then finally understand the advances in materials and processes, recent advances in the board level interconnections area. So with that, I would first like to talk about the interconnections in electronic systems themselves. So there is a hierarchy in the interconnections in the electronic system, starting from on the chip itself, so which is called as level 0, which is essentially on the chip. And after the chip is fabricated, we end up packaging the chip for multiple reasons, for getting the signals out and also to protect, mainly to protect the chip. And that is, the packaging is done, the connections are done using these different levels of interconnections. So the first is the chip level interconnections, which essentially connect the chip or the IC to the package substrate. And after that, once the chip is packaged, it is then attached to the motherboard or the PCB, printed circuit board, which is where the second level interconnections or the board level interconnections come into play. And then further, these multiple motherboards can be attached to another connector, which is the level 3, and then which can be further used in different applications. So we are going to focus on the board level interconnections or the second level interconnections in this course. And to distinguish between the chip level interconnections and board level interconnections, in a conventional package architecture, we'll first connecting the chip to the package using these chip level interconnections, and then finally connecting the package to the board or the PCB. The main difference in these two levels of interconnections is the size and the pitch at which they are made. The chip level interconnections are mainly much smaller than those at board level, and board level interconnections have a larger pitch ranging from anywhere from 300 to 1000 microns. And the process by which these interconnections are made or fabricated are different for these two. For instance, since the chip level interconnections can be made by plating or jetting, depth transfer, and they are for instance, the solder based chip level interconnections are mainly binary interconnections, binary materials which can be plated, whereas those used in the solders or the materials that are used in board level cannot are usually ternary solders which cannot be plated. So hence we use different processes to manufacture those. And the assembly and is again multiple different processes can be used for the chip level interconnections, whereas mainly mass reflow is used for the board level interconnections. An important distinguishable point is the reworkability, where on the board, when the package is attached to the board, almost always reworkability is required, and hence, which is a major reason why something like an underfill material, which is used to improve the reliability at chip level, cannot be used at board level directly. It is used in some cases, which we will talk about, but that is a major difference between these two. And another important aspect is the cost, where the cost for developing these board level interconnections is pretty low, and hence the processes need to adhere to the standard industry processes which have been established, which plays an important role in choosing the materials and the different processes involved in making these board level interconnections. So to start off, I'll talk about the two different types of board level interconnections. So the first is what is called as the plated through hole, which was used in the late 1900s, more or less, and then it's still being used, but not to a large extent. In this type, the devices which the devices have leads in them, and these leads are then placed into these plated holes on the PCB and are then soldered onto which are then soldered. So the the leads being inserted into these holes is what makes the electrical and mechanical connection between the uh, device or the component and the PCB. However, of late, the surface mount assembly is another type of interconnection that has taken over, which is now being used in a fair share of most of the devices. In this case, the devices, maybe the passive devices or the active microprocessor devices, they are mounted onto the printed circuit board directly and not inserted through the board, and they are mounted and attached using materials like solder paste and then reflowed to form a metallurgical joint. So since these are the more commonly used interconnections these days, we'll be delving deeper into this. And there are further, when we classify these, there are two types of surface mount assemblies. First uses a socket in which there is a socket which is attached to the printed circuit board through a mechanical contact. It can either be a mechanical contact or can be attached using a solder, and the packaged IC is then placed into the socket and is clamped on the socket, forming a mechanical contact with the socket itself. So the signal transfer happens from the IC to the package through the socket and into the printed circuit board. The second type of surface mount assembly is what is called as direct board attach, or SMT. And in this case, the packaged IC is directly attached to the printed circuit board using a solder paste. In some cases, in this case, we are showing a ball grid array, which we'll be talking about in just a minute. But the concept being that there is no socket in between between the package and the PCB, and the PCB packaged IC is directly attached to the printed circuit board. So since these two are the main types of as surface mount assemblies, we'll be talking about the main package architectures used in both of these. And in socketing, there are two main types of architectures that are used. First is called as the pin grid array. In this case, there are these gold-coded pins that are attached on the back side of the package, as you can see. So this is the back side of the package that is shown here. And these pins are then, the package is then flipped and inserted into the socket, where these pins go and get inserted into the socket and form a mechanical contact with the socket itself. And the socket is then placed on the printed circuit board. The second type of architecture, main architecture used, is the land grid array, where instead of pins, there are these copper pads which are coated with nickel gold coating, and this gold outer layer is there on the pads, and this package is then flipped and inserted into the socket, where excuse me, a stable mechanical contact is formed between these lands or these pads and the socket paddles. So in both these architectures, as I mentioned, a mechanical contact is formed with the socket, and which helps in the reworkability a lot, where since it's just a mechanical contact, the package can easily be removed and replaced with another package. The second package architecture that is used, the second type of assembly technique is SMT, or direct board attach. And again, two main package architectures are used in this case. First is the QFN, or quad flat no lead type package, in which there is a silicon IC which is which is encapsulated in a plastic material or a mold compound, and is then attached to these leads via wire bonding, which are these on the periphery of the package. And to attach this to the PCB, solder paste is used. Excuse me, solder paste is printed on the PCB, and then this package is flipped and attached on the PCB, and the entire assembly is reflowed, where the solder paste, it melts and forms a metallurgical joint with the printed circuit board. The second main architecture used in SMT, and which is the more widely used architecture, is the ball grid array. In this architecture, there are solder spheres that are attached on the back side of the package, as seen here. And again, the package is flipped and placed on the PCB. The entire assembly is reflowed, and the solder melts and forms a metallurgical joint with the PCB. So since this is the more commonly used architecture, we'll be talking more about this architecture in this course. So, but before that, why is this a primary board level interconnection technology, or what made it such a promising architecture? First, it is compatible with all different types of chip level interconnection. So the chip can be wire bonded to the package or flip chip attached to the package. It is still compatible with the BGA architecture for board level interconnections. Next is it can be formed into an area array, so which gives the possibility of high density interconnects, and a good small pitch between the solder balls. And also these solder balls, they have a small form factor, so they end up having, which brings me to the point of them having a shorter interconnection length, eventual shorter interconnection length as compared to the other architectures. So in this case, we can see the signal travels from the package to the socket all the way to the PCB, whereas in this case the socket is eliminated, so hence we have a shorter interconnection length, leading to better electrical and thermal performances. Also, solders have a relatively low melting point, and this can be processed at a low melting temperature, low reflow temperatures. Another important aspect of solders is the ability to collapse and self-align to the package and the pads on the package and the PCB, where when the solder is molten, it can, as I said, self-align with these pads, and has more tolerance to the non-coplanarities or um, the slight misalignments in assembly, and also a certain amount of tolerance to the substrate and die warpage. And finally, solders can be tailored to have high joint reliability, and are soft materials, so are capable of sustaining CTE, or coefficient of thermal expansion mismatch induced deformation. So now that we see why this is the primary interconnection technology that is used, we will delve deeper into the BGA fabrication and assembly process, how this interconnection is made. So this is what a standard schematic of a BGA package assembled on the board looks like. And if we look into one of the balls, it has a joint that is formed on the, it has a metallurgical joint formed on the package side and on the board side. So to start off with the fabrication process, it starts off with the final layer of the substrate design. So though this is still a part of the substrate fabrication process, the pad and the solder mask needs to be defined and needs to be designed to be compatible with the BGA. So we first start with the solder mask and surface finish or the pad design. Then we end up fabricating the ball or on the package itself, and finally do the board level assembly on the PCB. So I'll first talk a little bit about the pad design and the surface finish design and different types that are involved in there. So there are two main types of pad designs that are currently used, and which are based on the way the solder mask is deposited on the substrate. Solder mask is essentially a dielectric, which is the outermost dielectric layer on the package substrate and on the PCB. It essentially prevents the solder from spreading outside the required area. So if the solder has to spread only on the copper pad, the solder mask will make sure that it spreads only in that area and doesn't spread outside. So in this solder mask defined type of pad design, the solder mask itself covers about 10 to 20% of the pad area. From the top, if we see the copper pad is covered on the periphery with the solder mask. And what happens is that the exposed pad area ends up being slightly smaller than the final solder ball diameter. So the solder ball diameter here is slightly larger than the exposed pad area. The second type of pad design is the non-solder mask defined, or NSMD, or as it's sometimes called metal mask defined, wherein there is a gap between the pad and the solder mask, and the pad is essentially, or the copper pad is essentially 10 to 20% is made 10 to 20% smaller than that of the solder ball diameter. So if the solder ball diameter is 250 microns, the pad diameter will be about 10 to 20% smaller than that value. So in this case, what happens is the gap between this solder mask and the pad allows for more area for the solder to bond to the pad, and also it gives more space for the routing lines between the two different pads. So comparing SMD and NSMD, SMD type designs are usually used on the package side of the on the package side pads, whereas NSMD designs are usually used on the PCB side pads, and the main reason being that lower stresses are generated at the interface between solder and pad, owing to the higher contact area between the solder and the pad, and also it allows for more space for routing lines between pads. So given a choice between SMD and NSMD for the PCB side pads, NSMD is a preferred choice. However, with the SMD type designs, the solder mask being on top of the pad, it prevents any delamination of the copper pad from the substrate during processing, and which is one of the reasons it's used on the package side pads as well. Both have their disadvantages as well. In SMD case, higher stresses are generated at the sharp solder to pad interface, whereas in NSMD, since there is no covering of the solder mask on the pad, there is a high chance of delamination of the pad from the substrate during the processing steps. So looking at a cross section of an actual BGA, this is what an SMD type pad would look like and what an NSMD type pad would look like. So different OEMs and PCB manufacturers have their own specifications for the pad and the solder mask diameter. So while designing, it's advisable to look at those guidelines. And as a rule of thumb, as I mentioned, the exposed copper area will always be smaller than the solder ball diameter, And coming from a reliability standpoint, there are reports in the literature where the ratio is between the exposed pad area on the package side and that on the pad side. Having that ratio as 1:1 gives a good reliability, is what has been shown in the literature. So once the pad design and solder mask design is finalized, then we next come to the BGA manufacturing process. And solder paste printing is used as a very common method of manufacturing this BGA or fabricating this BGA. In this case, what this process entails is there are a metal stencil is designed, which mimics the pattern of the pads on the package, and the stencil is then placed on the package with the pads aligned to the apertures of the stencil. A solder paste is printed through the stencil onto the pads. The stencil is then removed and the substrate is reflowed, where the solder melts and forms the joint. And we'll go into this the details of this process in the next few slides. So this process is typically used for larger BGA pitches of more than 500 microns, and the smallest reported about 3 years ago, the smallest reported pitch was using this process was 400 microns with a 250 micron solder ball diameter. So to look into this process, first thing to look at is the solder materials, as in what materials can be used or need to be used to do this process. So solder BGAs are usually made using different solder alloys. Initially, tin lead eutectic was used to make the solder BGAs, but due to the ROHS, due to its non-compliance to the ROHS requirements, the industry has moved to lead-free solder alloys and in those the favorite choice is a tin silver copper alloys, like different tin silver copper alloys, due to their higher proven reliability and ability to control the microstructure during the reflow process. So there are different SAC alloys. SAC stands for tin silver copper, and there are different SAC alloys with different compositions of silver and copper which are used. So the nomenclature here shows that there is if SAC 105 means there's 1% silver and 0.5% copper. SAC 305 is a very commonly used alloy which contains 3% silver and 0.5% copper. These alloys have different melting temperatures but are in the similar range. They are higher than the tin lead eutectic, but these alloys are known to give the maximum reliability among the good reliability among the lead-free solder alloys. So once we have the solder alloys, the next thing to look at is what is a solder paste and how to get a solder paste. So solder paste is essentially a combination of two different materials. One is the solder alloy powder itself, the metal content, and the second is the paste flux. So when we mix these, we end up getting a solder paste. The typical metal loading in the solder paste is about 87 to 91 depending on the paste type, and the volume of the flux in this mixture is about 35 to 50%. So it's a pretty large amount of flux that is used in this mixture. The paste is what we call is a thixotropic material. It's a rheological property wherein what this entails is when the paste is sheared or a shear force is applied to the paste, its viscosity changes and it's easily flowable, whereas when that shear force is removed, it maintains its shape and it doesn't flow anywhere. It doesn't flow anymore. So it can be compared to something like ketchup, where when the ketchup is squeezed through a bottle, it's essentially a shear force is applied and the viscosity is lower, because of which it can flow. But when it's squeezed out onto the plate, it then doesn't change its shape or it stays in that place. So the solder paste acts in a similar way according rheologically. So the paste flux has different components which serve different purposes. It has activators which help in reducing the solder oxide during reflow or removing the solder oxides during reflow. The rosin resin which gives the rheological and the rheological additives which give the rheological property, and also solvents to dissolve all these into a solvent medium to dissolve the activators and to keep it in a liquid state. So that's what a solder paste is, and we will now look at what the solder paste printing process entails. So as I mentioned, the stencil is aligned to the substrate and the solder paste is printed. The printing occurs with the help of a squeegee, which is essentially a material which shears or pushes the paste through the stencil and applies that shear force that is needed for the paste to flow. So this paste flows and covers all these apertures of the stencil. And once the printing is completed, the substrate moves down to separate the stencil from the substrate. So when the substrate is moving down, what essentially we can see is there are two different forces which are acting. One is the adhesion of the paste to the stencil, and the second is the tackiness or the pull of the paste down to the substrate. So there has to be a balance between these forces such that most of the solder paste that is being printed should be transferred onto the copper pad and not stay on the stencil. And that is designed that to get that we design the stencil and the paste, choose the paste accordingly. So we'll talk about that. So in order to get that good transfer of paste, multiple things are important. One is the stencil design is important, and the material of the stencil is important. So in the industry, two main materials are commonly used. First is stainless steel and the second is nickel to manufacture the stencil. Then the stencil manufacturing process is also important. For instance, there are three processes that are widely used. First is the chemical etch, which is an older technology, which gives an undercut on both the top and the bottom, as can be seen here in the aperture. Laser cut stencil and electroform stencil are more newer processes which are more widely used these days, which give a pretty clean cut of the stencil and have better space transfer properties. Also, the more newer stencils can have some flux repellent nano coating that is applied on the stencil, which enables better release of the solder paste, printed solder paste, and that coating can be made with a fluoropolymer or this SAMP material, which is a monolayer, which is essentially helps in a fluxophobic or a flux repellent material. The second thing which helps in, which is needed to be looked at while designing a stencil to get a complete transfer of the paste is the area ratio and the aspect ratio of the apertures. Now, the aspect ratio of the aperture is essentially the width of the aperture, ratio of width of the aperture to the thickness of the stencil, and area ratio is the area of this aperture to the area of the stencil walls. So for these ratios determine the quality of paste release, in the sense how much paste will be released, which essentially, going back to the physics of it, will give a balance between the adhesion of the paste to the stencil to the tackiness of the paste, which will essentially let it stay on the copper pad itself. And for in the industry right now, with the stencils that are being manufactured, a good estimate for the aspect ratio and area ratio for these the stencils manufactured by different processes are mentioned in this table. Usually for a laser cut stencil, a stainless steel laser cut stencil, which is the most commonly manufactured stencil, an area ratio of greater than 0.66 is preferred to get a good transfer of paste, whereas an aspect ratio greater than 1.5 is preferred for a good paste transfer. So even when we finally decide how much volume of the paste needs to be printed to get a good BGA size or the desired BGA volume or desired BGA diameter, the stencil design is equally important to ensure that we end up getting that amount of solder paste on the board to get the desired volume. So now that we know what is required from a stencil point of view to get a good paste transfer, we now look at it from a solder paste point of view. And as I mentioned, the solder paste viscosity is a function of the shear force. So the viscosity will change at different stages in the printing process. So initially, when the solder paste is stirred and is put at close to the squeegee, the viscosity is lesser. When the squeegee is actually doing the printing, the viscosity goes down, and such that the paste can flow properly and fill all the apertures. And after the stencil is removed, the paste needs to recover and not flow anymore, because if it flows at that point, it's going to end up bridging with the neighboring printed structure, and it's going to form a bridged solder joint. So that's also, so the recovery of the paste is also very important, in the sense after the remove the stencil, the paste should stay in that state and not slump or flow after that. So the volume of the paste printed is also an important consideration. And as I mentioned, the volume of the flux in that mixture is very high, about 35 to 50%, and flux contains some volatile elements. So during the reflow process, these volatiles are evaporated. The flux, a lot of quantities of the flux is evaporated, because of which there is a significant volume shrinkage, and hence, based on the final volume of the ball or the bump that is required, we back calculate the volume of the paste that should be printed based on the volume shrinkage, and accordingly design the stencil apertures based on the volume of the desired volume of the paste. The next thing to look at is the solder powder sizes, which is the in the solder alloy powder is essentially made of tiny solder particles, and these are the particle sizes that are usually commercially available by different vendors, and they are named as different types of solders. So uh, for instance, type 3 will have an average diameter of 35 micron, whereas type 7 will have an average soldered particle diameter of 6.5 micron. Now, why is this important? It's because of the printing properties or the printing requirements, which comes from the 5-ball or 7-ball rule. Now, what this rule, it's essentially a thumb rule, it's a guideline. So what this says is, for a circular aperture, while printing the solder paste, to get a good print and to get good reflow after printing, there should at least be um, seven small solder particles in a row, uh, uh, diametrically. Diametrically. So what I mean by this is, for example, if it's a 250 micron aperture, stencil aperture that you are printing through, and you would at least want 7 of these tiny solder particles. So divided by 7, it's about close to 35. So the 250 divided by 7 is about 35. So the average particle diameter should be either 35 micron or lesser than that. So the preferred solder paste types that you would want to use is type 3 or lesser than that. So depending on the aperture of the stencil that the paste needs to be printed in, we would end up choosing the solder paste or type of solder paste. Similarly, for a rectangular aperture, it's more like a 5-ball rule instead of 7-ball rule, and the same concept applies. So after this paste is printed on the board, the next step is reflow, and in which the solder will melt. So this is a typical 5-zone reflow oven, which is used. There are, in the industry, 8-zone, 10-zone reflow ovens are also used, which have better control over the temperatures in different zones. So there are um, four standard parts that the solder paste goes through, or the solder goes through in the reflow uh, stages that the solder goes through during the reflow step, and those are preheat, soak, reflow, and cool down. So this graph here shows a typical solder reflow profile for the SAC 305 solder. What happens in the preheat zone is that the temperature of the board or the substrate, it increases slowly to a particular temperature, such that there is not a sudden increase in temperature preventing any thermal shock to the components. And once at reaching this temperature, it also removes the flux volatiles. And in the soak region, the flux is activated using the activators in the flux, and it essentially, activating means it will start removing the solder oxides on any of the solder's particles. Then comes the reflow, where the solder is actually molten, where we take it past the melting point of the solder paste, and then is the cool down stage where the joint is solidified and the microstructure is formed. So these are the stages of the reflow. So we have a short video here which essentially shows the solder paste printing process which was recorded in the lab. I hope I'm able to play the video. So essentially this is the squeegee, this is the stencil area, and this is the area where the paste that needs to be printed. So the board is aligned to this area of the stencil, and the solder paste is initially put at one end of the uh, printing pattern, and during the printing the board is aligned, it's inserted, the stencil goes down, and the squeegee goes down, it prints across the paste. We make sure we get a clean wipe or a clean print, and at the end we see the paste is printed in the pattern that was designed. And after this printing is done, the print is first inspected under optical microscope to see if there are any visible defects, like some missing areas of solder paste or some bridging, and then the board is after that which it is reflowed to form the solder joint. So during this reflow, there are multiple reactions that are occurring at the interface of the solder and the copper pad, which essentially end up forming the joint. And it depends on what surface finish is used on the pads. So surface finish is essentially a coating that is applied on the copper pads and the copper on the package and the PCB side. It can be compared to a UBM or underbump metallurgy that is used on the chip side for the chip level interconnections. So it's mainly applied to address the oxidation and of copper and provide a good wettability for solder, and also to it also controls the interfacial reactions that occur between the solder and the pad, which determine the joint microstructure and properties. So that's the pad. It's in the schematic is a surface finish, and during the reflow there's a reaction between the surface finish and the solder to form intermetallics right here. So with different surface finish, we get different microstructures. I've shown two examples here with surface finish called OSP, or organic solderability preservative. It is an organic material that is deposited on the pad and during the reflow, it gets dissolved, and the reaction occurs directly between the solder and the copper pad, leading to intermetallics formed, which are mainly copper tin intermetallics. Whereas another surface finish called INIPIG, or electroless nickel, electroless palladium, immersion gold, is what it stands for. It mainly forms nickel-based intermetallics between the uh, between the pad and the solder itself. So these are mainly two different types of intermetallics that can be formed with these different surface finishes. There are other surface finishes commonly used, such as electroless nickel immersion gold, or ENIG, ENIPIG that I just mentioned, which has another layer of palladium in there. OSP, which is an organic material, and also immersion tin is also commonly used. All these have their advantages and disadvantages. For instance, ENIG and ENIPIG, they have the gold outer layer surface, which gives a very good wettability for solder, and hence um, that is a major advantage. Also, the reaction control between nickel and solder is better than the copper and solder, which can form like very fast intermetallics. On the other hand, um, OSP OSP or immersion tin will end up forming copper tin intermetallics, which can be with the growth can be pretty fast. But however, the ENIC and ENIPIG are more expensive than as compared to OSP, and as we had initially mentioned, the cost is a major factor in board level interconnections. Many of these board level interconnections use OSP to reduce the cost, but for specific applications where the reliability is a very important aspect, there we would tend to use a better, more reliable surface finish such as ENIC or INDIPIC as compared to OSP. So it really depends on the final application of what surface finish you'd want to use. So at this point, we know that the BGA is fabricated, the solder ball is there on the package. Next is to characterize the process. So characterize the deposited BGA. And in order to do that, first process is X-ray characterization. In that, we mainly check for voids, solder bridging, and any missing solder balls. So for instance, in this image, you can see there are tiny voids in all these solder balls which are there. And according to the standard, it is void is considered as a defect if the area on an X-ray image is more than 25% of the solder ball area. So not all voids are bad, but it mainly depends on where the void is located. In the sense, even if it's a small void, but it's located at the interface of the pad and the intermetallic, then that is a prime site for crack initiation, and hence is not good. If it's located in the center, it's probably would be able to pass the reliability. Second thing is, so the voids are mainly created due to the flux volatiles. So when the flux volatiles, they evaporate during the reflow step, if there is not enough space for them to escape, they will get entrapped in that solder joint and end up forming a void. So that can be eliminated by optimizing the reflow profile and using something like vacuum assisted reflow processes to remove the voids completely. There are also bridged joints which can be seen and which can be improved by a better process control of the solder paste printing process and controlling the solder paste volume and stencil apertures. The next characterization process is shear test, where the solder balls are essentially sheared using the shear tool, and there is also a standard to be followed. So there are different shearing speeds that are used, and essentially we would want to get a low standard deviation, which means that we will have a well-controlled process. So for a SAC 305 solder joint, typically we would get, this is a commonly observed interface where the shear interface has partially solder and partial IMC or intermetallics on the shear interface, and a ductile fracture is seen. Whereas if in some cases with reduced solder volumes, or if the package is exposed to prolonged thermal stresses, then we can end up seeing a brittle fracture mainly through intermetallics, because the energy required for such a fracture is lesser, and with lower solder volume, that's what happens. So these are the two types of interfaces that can be shear interfaces that can be seen in a shear test. So at this point, the package is fabricated, the BGA is fabricated on the package is inspected. Next is the step is to do is the board level assembly. So to do this board level assembly, first on the PCB, of course the PCB is designed to have a pattern of the BGA, and then this pattern is fluxed, or a small amount of solder paste is printed on this on this pattern on the pads using a stencil. The BGA package is then picked and placed on this pattern, and the entire assembly is reflowed to form a metallurgical joint and to form to essentially form the solder joint. So when we look at the cross section of a BGA package, we'll have an array of these solder joints, and this is what an individual joint would look like. So at this point, we need to realize that at every reflow, there are more and more intermetallics that are formed at this interface. So the first time when the solder is attached to the package, there is a layer of intermetallics formed. The second time when the board level assembly happens, again the solder is molten, so there are intermetallics formed here, and these intermetallics grow. So all that needs to be considered while designing the surface finish and designing the interconnection materials and processes itself. So during this,
why don't we take a short break to see if there are any Q&As? Would this be a good time?
Sure, we can stop here. We can take
we are right at the middle of this short course.
Okay.
So there's already one question posted. The question is, why is delamination of solder with NSMD not a problem for PCB side?
Oh, so that's a good question, and it is a problem. So with the NSMD, that's a challenge that comes. But since the PCB on the PCB side, when you do the reflow and the processing, it's on one level of processing. It's like processed once, whereas on the package side, it is we prefer having SMD because it is processed initially during the package processing, and also then it is passed through the reflow during the board level assembly as well. So it goes through more process steps, which is why we would want that to be locked in. But definitely that is also a challenge in the NSMD. Pad delamination is also a challenge in the board side. However, it is still preferred because of the higher reliability that it offers to the solder joint.
All right, thanks, Omkar. Are there any other questions? Please either post it in the chat box or you can unmute your microphone and ask. There's one more question. There's a lot of research into low temperature solder alloys and processes. Any comments from soon to be Dr. Gupta?
Yes, sure. So that's a very good point, and I have a section on low temperature solder alloys later in the presentation, so I will be discussing that in some detail as well.
Okay, very good. I don't see any other questions, so why don't you go ahead and continue?
Sure. Thank you. So as at this point we saw that the assembly is done, board level assembly is done, and so during this assembly process, and not just this assembly process, but the entire fabrication process of the package, the chip level assembly and the board level assembly, there are many stresses that can be generated in different areas of the package itself, in different areas in different materials. So mainly these stresses and strains are induced because of the mismatch in the coefficients of thermal expansion between different materials. So for instance, the silicon chip, the organic package, organic board, or silicon package as well. So these stresses and strains lead to reliability challenges. And for instance, the CTE mismatch, it leads to the generation of plastic strains in solder materials. Here, so which is dependent, so the strains in these solder materials are dependent on the location of that solder joint and also on the CTE difference between the uh, chip and package or package and board, whichever level we are considering it at. So that's what these points say, that there is the CTE mismatch between the chip and substrate and PCB causes stresses and strains in these solders. And because of these stresses, when the packages are cycled and from low to high temperature, it leads to the solders undergo thermomechanical fatigue, and because of these high stresses, they can lead to cracking in these solders. So it is a major reliability concern. And as package sizes are increasing, they go up and the pitch goes down. It is even more of a concern because um, as I said, it depends on the length of the package as well. So farther the solder joint is, the more is the strain that is generated. So that's the CTE related stresses, strains, the stresses and strains. There are also warpage related challenges because of this CTE mismatch. For instance, during the substrate fabrication and chip level assembly, because of CTE mismatch, the substrate can be warped, and during the board level assembly, this can lead to multiple challenges such as non head and pillow defects, non-reflowed joints, uh, open joints, which we'll talk about it now. So the strains, the warpage strains, are usually generated during the interposer fabrication and chip related assembly process. And during the board level assembly process, this can lead to reduced assembly yields, mainly because defects such as head on pillow, where the solder paste on the package on the board is reflowed separately than the solder ball because of like oxides being formed on the surface. Then there is something called as non-wet open, where the solder paste gets merged with the solder ball, and it reflow separately, again, not forming a joint with the PCB, not wetting the PCB. Because of the joints in different areas, for instance, at the edge of the PCB, you can have something like a stretched joints, whereas in the center of the PCB, center of the package, where the warpage is lesser, we can have bridged joints. So squished or bridge joint. So all these lead to reducing the assembly yield and can actually cause major challenges. So to develop a process with controlled warpage, there are empirical formulas that have been described in literature and based on some JITA standards. So one of the empirical formula is the maximum warpage that can be accommodated is the solder ball height times 0.87. So it's just one of the empirical formula, but there are such empirical formula that are used while designing such packages. So because once we understand like these challenges, why do we need to understand these challenges is because one, to develop a process, and second, to get like a reliable process or a good reliability to get good reliability in these joints, because we want these packages to last longer. So to characterize for these reliability, what is commonly done is accelerated testing or environmental stress tests, where where this test is defined as this test essentially stresses the condition which stresses one or more conditions which the package will tend to undergo, and then accelerates the failure mode such that the time required to failure is reduced, and we can see what type of failure will the package go through if it in a regular operation. So an important consideration in reliability test is the intent of the test is to, as mentioned here, accelerate a given particular physical mechanism without introducing any new failure mechanisms in the joint. So what this image here shows is that if eventual result is to have a particular result as shown in this third picture, the accelerated reliability test should not lead to any new failure mechanisms such as those shown in these two pictures. It should accelerate this mechanism such that it happens much sooner. So that's the whole point of the reliability test. And the failure analysis that is performed is to understand what type of predominant failure mode occurs and the fundamental failure mechanisms. In the industry, usually a pass-fail criteria is used, but in order to understand the failure mechanism, the package needs to be taken to failure and then look at the failure mode. These are some of the examples of reliability tests. The thermal cycling test, where the package is cycled between low and high temperatures. Drop test, where it's dropped from a particular height based on different standards. High temperature storage. Highly accelerated test has like high temperature, high humidity, and sometimes even bias if that is to be applied. An electromigration test where a current is passed through the joint to see what kind of failure it occurs. So the tests really need to be these tests need to be decided as based on the application where the package is being used or the device is being used, and accordingly use different tests for different applications. So again, just to get a little bit perspective is electronics failing in the car is actually can actually be a much serious problem than dropping the phone in the pool, but a reaction as a user can be different to that, but just as a perspective. So as I mentioned, the choice of the reliability test depends on the application where the package is supposed to be used. So it depends on application, it depends on the stress levels that are being used in the application, and also the duration of application. For instance, in mobile packages, typically used for 2 to 4 years, it's at moderate temperatures and they have JEDEC standards for these tests, and drop tests and thermal cycling tests are more commonly used. For high performance computing applications, it's in continuous operation and moderate to high temperatures can be reached. And again, so because of that, thermal cycling, high temperature storage, and HASS tests are used on the packages for accelerated testing. Whereas for automotive electronics, they are used for a longer term, like 8 to 10 years. And if particular electronics under the hood can reach very high temperatures, and hence they have different standards set by the AEC or Automotive Electronics Council, and need for exceptional reliability, because we can't afford electronics in a car to fail when it's going at 70 miles an hour on an interstate. So the very high reliability is expected, and hence different tests like high temperature storage, thermal cycling, thermal shock, vibration tests, all are performed on automotive electronics. So based on the reliability tests, different failure mechanisms are just mentioned here. And for a thermal cycling test, you'll typically see fatigue cracks at the interface of the solder and intermetallic near the pad. For electromigration tests, you'll typically see small voids formed at the interface due to the current-driven diffusion, and which will eventually, over time, lead to the formation of cracks. And for drop tests, the main failure mechanism is pad cratering and RDL cracking, or RDL is the redistribution layer or the routing lines which can get cracked. So these are the typical failure mechanisms. And when we design the package, we want the package to pass all these reliability tests, and hence while doing the design, what we do is design for system level reliability. And essentially the method to do that is to use finite element modeling, is one of the methods to do that, to predict the reliability, performance, and accordingly design the interconnection system. So I won't go into the details of this. This can be a separate course by itself, but just a snapshot, or for instance, for thermal cycling, we look at the accumulated strains that are generated in the solder balls, and accordingly estimate the number of cycles to failure. For drop test, we look at the impulse stresses that are created in different areas, and then accordingly design the interconnection system. So at this point, I was going to have a break where we were, if anyone had any questions, but I guess we can, since we took a short break, we can take the questions at the end of the presentation. So till now, we looked at the process as a BGA fabrication process, reliability, what is standard.
Omkar, if I may
Yes,
interrupt,
Professor.
it's a good idea to take these questions because it's a short course.
Okay.
So there is one question that's been posted. It says on current slide, I see two IMC. Are they during the same bonding process or different?
Oh, this one. So the intermetallics that are formed in will be.
It's slide number 26.
Slide 26, yeah.
Oh, okay. Right. So the intermetallics are typically, as I said, they will depend on the surface finish that is used. So for instance, for example, if a nickel gold or ENIG surface finish is used on the package side, we will end up forming a nickel 310-4 intermetallic here. And if an OSP is used on the PCB, then it will typically be a copper 10 intermetallic, primarily copper 610-5 here. So this here is it's a representation of what the joint would look like, but the intermetallic form would typically be based on what surface finish is used.
So this joint has gone under two bonding process, 2 times?
Yes, exactly. So first would be when it is attached to the package, when the solder ball is attached to the package, and the second is when the package is attached to the board itself.
So in this case, the second bonding process should be at lower temperature than the first one, or it would be at the same?
No, it would be at the same, because the solder material is the same in this case. If it's the SAC 305 solder, for that to melt, we would want it to take it to the same temperature. And in this case, typically it's about 245 to 250 degrees max temperature. And so in that case, this the intermetallic on the substrate side will keep on growing at that temperature when this is being formed.
So have you seen any whiskers during this process or in other process you observed?
So yes, 10 whiskers. 10 whiskers are observed, but depending on the surface finish used, as I mentioned, if immersion tin is used, that is a problem. But yeah, so 10 whiskers are definitely an issue which can, if not during the reflow, over time.
Connections repairable or the part needs to be scrapped?
So bridge, that's a good point. So bridge connections, you typically, we cannot modify them at as is. So the part will have to be removed, or what we call as rework, in the sense the solder is melted. That's what the reworkability aspect comes in. So the part needs to be removed, the solder needs to be removed, and then reballed. If the part has to be conserved, then the BGA will have to be reballed and then reattached.
Thanks, Omkar. There are no more questions, so please continue.
Okay, thank you. So as I mentioned, we looked at the standard process till now of the BGA fabrication and assembly. Moving forward, like this is taken from the heterogeneous integration roadmap, where the BGA interconnections, for the BGA interconnections, the pitch for different applications is expected to go down, and the package sizes are expected to go up higher and higher, and that will lead to more and more reliability challenges. For instance, the smaller BGA pitches will lead to a scalability limit for solder paste printing process and for the BGA manufacturing, and hence newer processes need to be looked at for the BGA formation. Also, more issues of solder ball bridging during reflow can be seen because of the reducing pitches, and which leads to a necessary reduction in the solder volume. But reducing the solder volume will again lead to challenges with reliability. Not just with this, but this trend to thinner and larger package substrates will also aggravate the warpage even more, leading to degrading yields in the board level assembly because of the reasons we just mentioned. And the solder strains in these are also expected to increase because of the large CTE mismatch between the package. Excuse me. Solder strains are also would be expected to increase because of the large CTE mismatch between the next generation low CTE substrates, and reduced solder volume and non-uniform joint shape. So these are all the challenges that the BGA interconnections would face. So firstly, for the smaller BGA pitches, techniques like ball drop are used or can be used. In this technique, it essentially overcomes the limitation of solder paste printing of reduced pitches, where in this technique, preformed solder balls are used. So if we want to 200 micron diameter solder ball, a preformed 200 micron diameter solder ball is used, and those balls are directly placed on the substrates using different methods. So in order to do that, a tacky flux or a minimum amount of solder paste is printed on the pads first. The balls are dropped. These preformed balls are dropped using different methods. In this case, we're showing it's dropped using a stencil, where such that one ball fits in this one aperture, and then the balls are reflowed to form the joint. So that is one. As I mentioned, it overcomes the limitations of paste printing at smaller pitch. So different methods for ball drop. First is ball drop using stencil, that just said. So we print some tacky flux on the substrate, align this ball drop stencil to the pads, and then do the ball drop using like dropping one ball on the at a time, and then reflow to form this joint, to form the joints. Next is what is called as vacuum transfer ball attach, where there is a vacuum tool which is attached to a vacuum tool head, and it essentially picks up the balls from a reservoir of solder balls, and such that there is one ball that is held in each aperture. This vacuum tool then goes and aligns with the substrate, and that is aligned. The vacuum is released and the tool is lifted such that the balls stay down, and then the entire thing is reflowed again to form a ball, to form the joint. Next is something called as jetting, where there is a jet-like funnel where there is a reservoir, solder balls reservoir on the top, and one single solder ball is released at one time so that it comes uh, on the pad, gets attached. So it can be individually dropping and then eventually doing the reflow, or dropping one ball doing a laser reflow. Either way, both ways are been explored. And the fourth is what is called as a gravity dispense ball attach, where package is balls with the loaded tray cavity. So there's a tray cavity here, and a substrate with tachyflux is brought in contact with this such that the substrate has only the tray cavity is aligned to the substrate, and the balls from this cavity go and sit exactly on this fluxed substrate, and is then removed such that and then reflowed such that the solder joint is formed. So these are some of the techniques, ball drop techniques, which can be used for reducing for the reduced pitches. The next, for warpage mitigation, stiffeners or lids are metal stiffeners or metal lids are used. So what a stiffener essentially does is it's a metal ring that is attached on the periphery of the package, and it provides mechanical stability and reduces warpage during processing. And sometimes where packages generate a lot of heat, a lid is also used where it also helps in removing the heat from the package. So this is one of the solution for warpage. Other solution is using low temperature solders, and the important attributes of these low temperature solders are that the melting point of the lead-free low melting solders is the melting point is between 130 and 190 degrees Celsius usually. So they end up having to have a lower peak reflow temperature, not as high as SAC solders. So it reduces the warpage as there are lesser thermal stresses during processing. Also, they have lower energy consumption, which essentially leads to a lower carbon footprint and lower cost because of lower energy consumption during processing. However, many of these low temperature solders, they have reliability concerns because during thermal cycling, during thermal aging and drop test, because these low temperature solders are mainly based on two materials. One is bismuth and indium, and bismuth by itself is a more brittle material, because of which the thermal cycling reliability is reduced. And indium based solders have, since the melting point of indium is much lower, so the indium based solders have a very low temperature, so sometimes it can be below the operating temperature range, in which case these solders cannot be used, but they are alloyed with different elements to improve the reliability of these solders, which we'll be talking about in the next few slides. So the applications of these low temperature solders are such that one, where they are used as a paste. So the low melting solder paste, for instance, in this case, for example, a tin bismuth solder paste with a melting point of 138 degrees Celsius is printed on the board, and the SAC BGA package with the standard SAC solder ball is attached to the board, and then the reflow is done at a lower temperature. It's not done at a standard 250 degrees Celsius, which is required for SAC. So at say for instance, the reflow peak temperature would be around 170 degrees Celsius. At that point, the most of the SAC core remains unmelted, but what happens is that the tin bismuth solder on the bottom, that melts and fuses with the SAC core, giving the joint. So we have like a mixed microstructure here with an unmelted SAC region and a bismuth diffused region. So again, as I said, the reliability of these is still being explored, and the ways to improve reliability is very much an area of research for these solders. Another method by which these are used is, or the advantage of low melting solders is taken is having coatings on the sac sphere, such that in this case, bismuth is coated on the SAC sphere on the outside, and when the ball is placed on the package and the reflow is done, again the peak reflow temperature is much lower than sac reflow temperature. In this case, it was about 200 degrees Celsius, and the from the tin from the solder core reacts with the bismuth on the coating, and it forms that eutectic system. It forms that eutectic melting system, and which is what essentially bonds with the pad. So we have a bismuth diffused region on the outer surface of the sphere and an unmelted sac core, but the joint is still formed. So these are some of the ways in which the low melting solders have been used for controlling warpage and during assembly. The other ways to so that was to look at warpage. Next was, we also said that there are a lot of stresses and strains that are developed in the packages. So some other strain relief mechanisms are used, such as compliant interconnects or doped solders, which I'll be talking about. And polymer collars and reworkable underfills are also materials that are used for helping with this increased strains that are developed in the solders. So as for compliant microstructures, these are essentially small structures that are deposited on the or that are fabricated on the pad, which help in absorbing the stresses that are generated, so that the solder by itself doesn't have to absorb all the strains that are generated. So for instance, in this case, there is an elastomer or a silicone bump that is placed under the solder, which helps in absorbing some of the stresses. These are different interconnect structures, which again do the same role of helping distribute these stresses and not letting the solder absorb all the stresses, which improves the life of the solder. For reworkable underfills, these are materials which allow for the device rework after curing. So what these essentially do is they are like underfills, but if the device needs to be reworked, they can be removed and then the rework can be possible. So this is some of the solution that is used for mitigating strains, since underfill will help in mitigating the strains and distributing the strains. Polymer collars are like thermoset materials which are spin coated on the BGA such that they form a collar-like structure right here, which also help in improving the reliability performance, again by redistributing the strains, so such that there is whatever strains are developed at this sharp edge of the BGA to the pad can be redistributed in the polymer itself, so which helps in improving the reliability performance. So when looking at reliability again for these newer products, there is a, for instance, for example, in mobile products, there is a key key challenge between improving both drop test and thermal cycling reliability, because both need both drive different areas, different stresses, and both need different abilities in the solder to accommodate those stresses. So for instance, in drop test, the ability should be to absorb the shock energy, whereas in TCT reliability, the solders need to have the ability to prevent plastic deformation. So if you're looking at it from a material standpoint, for drop test reliability, soft solders with lower modulus will have a better shock absorbing property, whereas for TCT reliability, a higher yield stress or higher modulus would be better for getting better TCT reliability. So there are material innovations that need to be done to achieve high drop test and high reliability. And one such example is doped SAC alloy, which was presented a few years ago by Indium, which has this manganese doped with manganese, SAC alloy doped with manganese, which provided a good drop test and TCT reliability. So that's one of the examples. There are other dopants available as well, such as cerium, titanium, nickel, which have been explored, where the SAC or the tin bismuth solders, they are doped with very minute amounts of these alloys, such as maybe typically less than 5%. So it can range anywhere from 0.1% all the way till 5%, and which help and improve the reliability. And the way this happens is that these dopants, they lead to some grain size refinements in the microstructure. In some cases, they slow down the intermetallic formation growth, which helps in slowing down the crack propagation. And also sometimes they change the plastic deformation mechanism and end up improving the ductility of the solders. So the mechanisms by which these dopants can help in improving the reliability, and this microstructure leads to better fatigue and drop test performance in these solders. So these can be used in both the regular SAC solders and in the low temperature solders as well. So these are some of the innovations that are done in the solder material space and the BGA space. So we've looked at the BGAs till now and how they are a major interconnection technology that is being developed and is widely used. However, having said that, the recent market trends, that when we look at the recent market trends, we also see that though BGA is definitely very widely used and is expected to be used in the near future as well, the need for sockets is also expected to increase in the near future. So even by socket type, the production sockets are expected to increase, and even the application space, in most of the applications, the need for sockets is going to increase. And with sockets comes the need for using technology such as LGA or PGA, more likely LGA because that's the newer the more widely used technology. So what happens then? Like, as I mentioned, like in LGA, this package is latched in a socket to form a mechanical contact, whereas in BGA, this package is attached on the board to form a metallurgical joint. So in many cases, what happens is that the same processor IC or the chip needs to be used in these socketing applications and these board level or SMT applications as well. But in order to do that, the OEMs or the manufacturers, they need to have two separate design cycles, fabrication cycles, assembly processes separately for these LGA packages and BGA packages, which is not only expensive, but it's like a lot of different processes, right? So there is sort of a need to develop a single BGA technology which can be used in both socketing and SMT applications simultaneously for the same processor IC. So then the question arises, like, if sockets are also being used, why can't we directly use a BGA package in a socket? As in, why go to an LGA package at all? Well, that is because there are multiple reliability challenges that the BGAs can face in a socket. First is, as we said, that BGAs are soft materials and the socket pins are pretty hard materials. So the BGAs can be easily damaged under the socket contact forces. And also, like, over time, the solders or the BGA solders, they react with the socket paddles to form intermetallics at the interface or surface oxides, and they increase the contact resistance at the interface. So it leads to large number of electrical losses. So hence, at Georgia Tech PRC, we have been working on a system where we develop a BGA based interconnection system which can be used both simultaneously in socketing and SMT applications, and we do that by a surface modification of the solders by metallic coatings. So we essentially take a solder ball and then coat it with like a multi-layered coating, such that it can be used in both socketing and SMT applications. And for that, we have two approaches. First is an approach where we use a conventional diffusion barrier noble metal coating, such as a nickel gold coating. And a second approach where we use, it's a more innovative approach where we use a bismuth gold coating, or which essentially forms a eutectic system between the solder core and the coating. So we start off with doing the coating design by looking at what reactions can occur between the core and the coating material, and at different stages of operation during socketing and SMT applications. Then look at the performance or the mechanical performance of that coated sphere and in a socket by doing some contact modeling, and also estimate the thermomechanical reliability performance of the the assembled package in when it is used in SMT applications. So this is some of the work that we have done, and I'm just giving snapshots of this work. It's if for more information, I'll be happy to talk in more details, or also can be more information can also be found in these published papers. So after the coating is designed, we then end up fabricating these spheres and packages. So we deposit the coating on these spheres by a combination of sputtering and electroless processes, deposition processes, and then develop a process for ball attach of these joints onto the package using a solder paste. At this point, there was a challenge that was faced where during the reflow, there is a there is a gold outermost layer on this coating, and during the reflow, because the solder paste wets the gold surface very well, the entire coating wicked to the top surface of the sphere. So in order to prevent that, we came up with a solution of using a polymer collar as a barrier layer material, as a mechanical barrier material, so which physically prevents the solder from diffusing to the top surface of the sphere. So initially the process of reflow was optimized to prevent this diffusion of solder to the top surface of the sphere, and when the package was used in socketing, we could see that the diffusion continued, and more diffusion was observed of this solder to the top surface of the sphere, so hence the polymer collar was used as a mechanical barrier to prevent that diffusion. And then finally, this performance of these coatings was demonstrated in both socketing and SMT applications, where we placed the package in the socket and applied a normal force from the top to see that we could get sufficient contact area between the solder sphere and the socket paddle. And when used in SMT applications, or after attaching it to the board, the packages were able to survive in different configurations of packages were able to survive up to 750 thermal cycles. Although there were some issues with this coating, well, like we could see a lot of voids due to the volume shrinkage, and we could not get rid of this intermetallic shell. We then proceeded to look at the second approach, which was the bismuth based approach, where though that coating would sustain the socketing applications during the SMT board reflow, it would essentially melt the entire solder joint because of that eutectic formation, and give the complete ball collapse. So that is something that we're still working on and is a part of the future work. So with that, I would like to summarize the talk, what we discussed from the beginning. First, talked about the board level interconnections and why they're important, because they are the ones that help in the signal transfer from the package all the way to the board, and also help in connecting different ICs. Why the BGA architectures are used, because of the small form factor and the shorter interconnection lengths over the other counterparts like sockets. Then we talked about the BGA fabrication by solder paste printing, and understood the importance of stencil technology, the way it is manufactured, then the role that the paste viscosity plays in the paste printing and how to determine the powder size to be used for paste printing. We talked about the solder reflow and the reflow process, design of the reflow process, that the reflow temperature should be higher than the solder melting temperature, and what the difference, how the different stages in the reflow what the different stages in the reflow process do to the solder paste, and the importance of surface finish. While choosing the surface finish, how to control the intermetallic reactions during the reflow. Then we talked about the board level assembly and importance of reliability, system level reliability. What are the different failure mechanisms that can occur? And for different applications, what are the accelerated reliability tests that we should look at? Last was we looked at some of the recent advances in processes, how the ball drop process can overcome the challenges of the solder paste printing process. Then from a material standpoint, how the stiffeners and low temperature solders, they address the warpage issue. And polymer collars, reworkable underfills, and doped solders address the TCT reliability or solder strains issue. Finally, talked about a little bit about the socketable BGAs or the work that we are doing at Georgia Tech. Finally, I would like to acknowledge Professor Vanessa Smet. She has been a very big part in this, played a very big part in this presentation. Some of the slides were, she's contributed to the slides and in building this presentation. Siddharth and Professor Swami for giving feedbacks on the presentation, and then the work presented done at Georgia Tech was done in coordination with SRC and Intel. So I'd like to thank them. With that, I would be happy to take any questions. Thank you.
Thank you, Omkar. Thank you for a very nice presentation. So we have one question in the chat box. It says, I found to my surprise that BGA packaging required design and fab of a custom substrate. Are prefabbed BGA substrates available that accommodate chips with a given pin count in the same way as PGA ceramic packages, for example?
So that's a good question. So when I meant that, what I meant by designing the BGA package is based on certain application or for whatever that BGA package is designed for that requirement. So typically it would be designed, it will be designed by the OEM for a specific chip or for a specific type of chip. So for instance, if say a company like Intel is developing their chip, they would have a standard BGA package for that chip that is designed to be used in for all those types of chips, so for all similar types of chip, because that would essentially need to have all the IOs connected from the chip to the BGA. So it's the what I'm trying to get at is, if there is a chip design that is done, then a similar package would be designed for that particular chip design. So in other case, if that's not the case, then that would be there would be a possibility that all the IOs from the chip are not connected or are not routed out to the individual solder balls. Does that answer the question?
Sure. Thank you. Thank you, Omkar. Several years back, there was work going on in trying to develop a programmable BGA package where the BGA package itself is a standard, but you get to program it in some way. I'm not sure what is the status of that now. There's another question. It says, how do polymer collars and compliant microstructures affect reworkability?
Oh, that's a good question. So polymer collars are typically not reworkable, like they are thermoset materials. Once they are deposited, then it's difficult to remove them. So that would make the package not reworkable, but so that's why they would be used in a case where the package is definitely attached to the PCB without, like, when it's not being taken out. So if in that case, if the reliability is poor and there still needs to be a reworkable solution, then over polymer collars, reworkable underfills would be chosen as the method to uh, help with that. With the compliant interconnections as well, it's so the compliant interconnections, as I can bring out the slide, it's more like on the um, on the package substrate, like between the package and the solder ball itself. So that is again, it would still help with the reworkability, because the solder can still be reworked, can still be remelted, and the entire package can be reworked, since the compliant interconnection would be at the base and it's connected to the package and not to the board, not the board side. So that would still be reworkable, but yes, with the polymer collar, we would not have as much reworkability as the reworkable underfills.
I think, Omkar, with that, we need to stop here because I think we are over our time by 3 minutes or so.
Okay.
So let me thank you again for giving this excellent short course, and thank you for all of the participants for joining us today. So please stay tuned. Every couple of months we pick a topic and then have a short course related to that, all in packaging. With that, thank you so much. Take care.
Thank you.
Bye-bye.